Once we've drawn the Lewis structure of a molecule, we can determine its geometry. And its geometry is really important for how it acts and how it reacts as well. So the first step to determining the molecular geometry is to determine its electron geometry. To find that, it's helpful to find the electron domain number. And to find that, you need to have Lewis structure. Now, we drew the Lewis structure of all of these in a previous video. So if you're curious how to get these, then you can watch that video. So silicon tetrachloride looks like this. His Lewis structure looks like this. When we're talking about the electron domain number, I'm going to abbreviate it ED, we want to know how many groups of electrons there are around the central atom. If they're bonding electrons, then we're interested in how many atoms it's bonding to. And if they're lone pair, then we just want to count the number of lone pairs. So in this case, silicon is bonded to 4 different atoms. We can erase these bonding electrons and in its place put bonds. And we can easily see that it's bonded to 4 atoms. There aren't any lone pairs on the silicon, like that would be like this or something. Since that doesn't exist, that means that the electron domain number is equal to the number of atoms that silicon is bonded to. So in this case, the electron domain number is 4. Now, the electron domain number is always associated with a specific electron geometry, which I'm abbreviating EG. The electron geometry associated with the domain number of 4 is tetrahedral. That means that the atoms, or if they're lone pairs, will arrange themselves around the central atom in a tetrahedral shape. In this case, since there aren't any lone pairs on the main central atom, the molecular geometry will equal the electron geometry. If there are no lone pairs on the central atom, this will always be the case. So that means the molecular geometry of silicon tetrachloride is also tetrahedral, which means that now you don't have to be able to draw the shape, but if you were to draw it, one of these chlorines would be coming out of the page, one would be going back, one would come up, and one would go off to the side. And it would give it a shape like this. Each of these, again, you don't have to memorize these bond angles, is about 109 degrees away from every other one. So they're spread out around that central atom as much as they possibly can be. Silicon dioxide has the Lewis structure that looks like this. Now silicon dioxide, if we want to calculate its electron domain number, it is only bonded to 2 different atoms. So silicon is bonded to 2 oxygens. There aren't any lone pairs on the silicon, so that means the electron domain number is 2. Now it's often confused and thought that that should be 4 since these are double bonds, but we're not interested in how many bonds it's making. We're interested in how many atoms it's bonded to. So the electron domain number in this case is 2. If the electron domain number is 2, then the name that we give it is linear. So an electron domain number of 2 is always associated with the shape linear. And in this case, there are no lone pairs around that central atom, so the molecular geometry and the electron geometry are the same. So silicon dioxide is a linear molecule, meaning that this angle between the oxygens is about 180 degrees, and silicon dioxide is just a straight line across. Sulfur trioxide, now this is the one that had a resonance structure, so when you're drawing or thinking about its geometry, it doesn't matter which resonance structure you choose, as long as they are all relatively the same. Okay, and I won't give you any that aren't. Okay, so if we want to calculate the electron domain number, in this case, sulfur is connected to 3 atoms, 3 separate oxygens. And so it has an electron domain of 3. So there's no lone pairs, and it's connected to 3 atoms, so that gives it an electron domain number of 3. If its electron domain number is 3, that electron geometry is called trigonal planar. Trigonal because there's 3 things it's connected to, or it's like a triangle, and planar because it's flat. That means nothing's going in or out of the page, it's just flat. And in this case, like the previous two, there aren't any lone pairs around that sulfur in the middle, so the electron domain, or the electron geometry, and the molecular geometry are the same. They're both trigonal planar. The Lewis structure of nitrogen trichloride looks like this. In this case, when we look at the electron domain number, we see that nitrogen is bonded to 3 different chlorines, but it also has a lone pair. So that gives it a total electron domain number of 4. Now we've seen that electron domain number before. That 4 is associated with the electron geometry of tetrahedral. But in this case, there is a lone pair on this nitrogen, so it won't look tetrahedral. When you're looking at the molecule, you only see the atoms. You can't see that lone pair up there. It looks like this. You only see the atoms. And so we can't call it tetrahedral because tetrahedral would look like this. So it gets its own name, and we call it trigonal. Again, it's trigonal because it's connected to 3 atoms, but this time it's trigonal pyramidal, because those atoms arrange themselves in kind of a pyramid shape. They're bent downwards because of this electron group pushing down on those bonds. So it looks a little bit like a pyramid. Sulfur dioxide has a Lewis structure that looks like this. This is another one with a resonance structure, but we're just going to pick one of the structures to work with. They should both give you the same results. Electron domain number here is sulfur is bonded to 2 oxygens, and it has 1 lone pair. So it has an electron domain number of 3. An electron domain number is called, an electron domain number of 3 is called trigonal planar, because it's like a triangle. But this one has a lone pair, and so its electron geometry and its molecular geometry will be different. If you think of these lone pairs as pushing down on these oxygens, then you can visualize this sulfur more like this. And we call that, very eloquently, bent. And lastly, let's look at oxygen dichloride. Oxygen dichloride has a Lewis structure that looks like this. If we count up the electron domain, oxygen is bonded to 2 chlorines, and it has 2 lone pairs. So that means it has an electron domain number of 4. An electron domain number of 4 is called tetrahedral. Because it has these lone pairs, the molecular geometry is not going to be tetrahedral, because we won't see these, but they still act on this. So this looks linear, but it's not. These lone pairs are pushing on those chlorines, and they push it so that they are about 109 degrees away from each other, just like in the tetrahedral geometry. So the molecular geometry for this one is also called bent. And those are the 6 molecular geometries that you'll want to be familiar with.